Okay, let's talk about a two-force body. So consider you have some object. This is a plate. It's subjected to two forces F1 and F2. So you have this plate. It doesn't matter the shape. There's a force F1 coming off this direction and a force F2 going off in this direction. Well, for static equilibrium, what conditions have to happen for static equilibrium? The sum of the forces must be zero and the sum of the moments must be zero. About any point, right, for the sum of the moments. So let's pick an arbitrary point. Let's pick point A right here. Okay, in order for the sum of the moments to be zero here, what is the moment of this F at this point? It's going to be zero, right? The moment arm is zero. So the only way for the sum of the moments to be zero is this F also has to pass through that point. So the line of action of F2 has to pass through A. So we have to line that up to this point. So now this force passes through A and this force passes through A. But now let's say, hey, you know what? The sum of the moments at A needs to be zero, but the sum of the moments at B also needs to be zero. Well, now this one passes through B, so that's fine. But this one, the only way we're going to get this one to have no moment about B is if you rotate it around so that this force, the line of action of this force, also passes through B. So what we're going to find is that the two forces have the same line of action. Well, if there's two forces and they have to have the same line of action, the forces must be equal and opposite. Otherwise, it's going to have a translational effect. So what is the upshot of all that? It's F1 for a two-force body. F1 and F2 must have equal magnitude but opposite sense, and they must lie on the same line of action. This is going to come up a lot. It's going to come up a little bit more when we start doing trusses and frames, but this is huge. That if you only have two forces acting on a body, regardless of the shape of the body, regardless of what it looks like, if there's only two forces, then you know the direction. You know that they must be equal and opposite in sense, and you know that they must lie along the same line of action. Okay, now this one, I find this one honestly a little bit less useful. It's nice to know, but it's a little less useful. And this is equilibrium of a three-force body. So now let's talk about our rigid body potato subject to forces acting at 3 points, right? So we have force here, here, and here. Okay, we're going to take that same approach, right? We're going to say, hey, some of the moments about some arbitrary point. We're going to assume that F1 and F2 pass through a single point. Okay, so if we take the sum of the moments here at D, then F1, the moment from F1 must be 0 and the moment of F2 must be 0. Now, the only way for this one not to add, F3 not to add additional moment, is that its line of action has to also pass through D. And so the upshot of all that is that for a three-force body, there's two options. Either all the forces must be parallel. In that case, you'll notice that none of the moments don't cross each other. So all the forces must be parallel. Or all three forces must intersect at a single point. Now, quite frankly, you could do a lot of these problems and never know that, and I generally don't refer to this, but you should know. You should be aware in the back of your mind that for two-force body, you definitely need to know the two-force body. You need to know this. For a two-force body, the forces F1 and F2 must have equal and opposite magnitudes and the same line of action. For a three-force body, it's good to know that there has to be one single point where all the forces pass through in order for it to be in equilibrium. Okay, so now let's talk about in 3 dimensions. So we talked about all this stuff in 3 dimensions, or in 2 dimensions. Now we're going to go into 3 dimensions. So 6 scalar equations are required to express the conditions for equilibrium in the general 3-dimensional case, right? Are some of the forces in x, y, and z all have to be 0, and are some of the moments about the x, y, and z axes all have to be 0. Well, these equations can be solved for no more than 6 unknowns, which are usually, when you cut through something, it's that type of represent reactions at supports or connections, okay? And you can write the vector version of this equation simply with the sum of the forces. Our vector sum of the forces is equal to 0, and our vector sum of the moments is equal to 0. So you'll notice we go from 3 equations and 3 unknowns in 2D to 6 equations and 6 unknowns in 3D. So it gets quite a bit more complicated. Conceptually it's not a whole lot different, but mathematically going from 3 unknowns to 6 unknowns and going from 3 equations to 6 equations is quite a bit of a jump. So let's talk about our 3D connections and supports. So in 3D we have the potential to resist up to 6 unknowns, right? So first off, a ball or a frictionless surface. Again, this only does one thing. It resists force in the y-axis. Okay, a cable, it resists force along the line of action of that cable. You don't necessarily, you can use information of the cable to know what direction that is. So these are one unknowns. Well, now we have two unknowns. We have a roller on a rough surface or a wheel on a rail, right? So it's going to let it go this way, but it will not let it go in this direction, and it will not let it go in this direction. Same deal. It will not let it go in the y or in the z axis. And so these are the two unknowns. You can have three unknowns. A ball and socket. This is a pretty common one, right? It doesn't let it move in x, y, or z. It can rotate all over the place. It can spin, but it can't translate. Same deal with the rough surface. But now here's where we have, this is the joy of getting into 3D, so we start to have even more. So a universal joint. Well, a universal joint, it will resist force in x, y, or z, but it will also resist moment in one of the directions. So if you were to try to rotate this about the x-axis, it's going to resist that. If you were to try to turn this about the y-axis, it'll collapse on itself. It won't resist that. Or the z, same deal. But in the x, it'll resist that. Take it to one extreme, a fixed support in 3D. You're going to have six unknowns: the moment in x, y, and z, and the force in x, y, and z. You have bearings. These are going to be common throughout this problem. Hinge bearings supporting radial load only. So like this is a good example. Like kind of consider a fence post, right? That it can go up, it could slide in this direction. So it's not going to resist force in this direction, but it is going to resist force in the z and y direction, and it's going to resist moment in the y and z, but it's not going to resist moment about the x. It can spin all at once in that direction, but it won't spin in other directions. Same deal with this. And then you have other ones like this where we will say that the hinge bearing with the zero, this one say does not resist lateral load. This one does resist lateral load, so you can have an additional unknown there. This is a door hinge. Hopefully that looks pretty familiar. It doesn't want to let things move this way or this way. Or in the y, it's going to resist x, y, and z. It's going to resist moment in the y and the z, but it will let it move in the other direction. So these are all different things. So there's no trick to this. We're not trying to be tricky and asking you. I'm not going to go out of my way to ask you problems about which direction will this resist force, but you need to be able to look at these connections. When you're drawing a free body diagram, you're going to cut through these things, and you need to know, hey, I cut through a fixed support. Well, that fixed support had the potential to offer something in all six unknowns, so I need to make sure I account for those. Okay, we're going to do another example, example 4.8.